Space is the grandest of all theaters. When we look up into the night sky, we are not just seeing twinkling lights against a dark backdrop. We are peering across unimaginable distances and back through aeons of time. It is a place of profound beauty and even more profound mystery. Among the most captivating of these mysteries are the concepts of black holes, wormholes, whiteholes. These are not just ideas from science fiction. They are born from the very mathematics that describes our universe. In this exploration, we will use simple words and trusted knowledge from organizations like NASA to gently pull back the curtain on these cosmic enigmas, inviting you to wonder with us about the true nature of reality. These three phenomena represent the extreme limits of our understanding. They challenge our everyday intuition about space, time, and matter. A black hole is a region of such intense gravity that nothing, not even light, can escape its clutch. A wormhole, still purely theoretical, is imagined as a spectacular shortcut, a tunnel connecting distant points in the cosmos. Let's begin with the most familiar of our cosmic trio, the black hole. In simple terms, a black hole is a place in space where gravity is overwhelmingly strong. Imagine throwing a ball into the air. It goes up, but Earth's gravity pulls it back down. Now imagine you could throw it so fast it never comes back down. Escape velocity. A black hole's gravity makes escape velocity faster than light. Nothing can travel faster than light, so once something falls in, it can never, ever get out. That's why it's called black. It traps all light. How does one form? The most common way is the death of a massive star. Stars are in a constant battle with themselves. Nuclear fusion in the core creates an outward pressure. Gravity relentlessly pulls inward. For most of a star's life, these forces balance. When a very large star runs out of fuel, the outward push stops. Gravity wins catastrophically. The core collapses under its own weight, squeezing huge mass into tiny space. That creates a stellar mass black hole. This is one of the most violent events in the universe. The outer layers are blasted into space in a supernova. The explosion can briefly outshine entire galaxies. Left behind is a collapsed core, a silent, invisible point of extreme density warping space. NASA's Neil Gehrels Swift Observatory detects the gamma-ray bursts from these events, giving us a front-row seat to black hole births. There are other types of black holes. At the center of nearly every large galaxy lurks a supermassive black hole. When we talk about a black hole, we are often referring to two key components that are defined by its gravitational field. The first is the famous point of no return, the event horizon. The event horizon is the black hole's boundary, not a surface you can touch. It's an invisible line in space. Outside it, a powerful rocket could still escape. Cross it, and your fate is sealed. Gravity becomes absolute. All paths lead inward. Imagine you're in a canoe on a calm river heading for a huge waterfall. Upstream, you can paddle to shore. Closer in, the current strengthens. At some point, you cross an invisible line where paddling won't save you. You go over the falls. The event horizon is exactly like that line. Beyond it, escape is impossible, even for light. This boundary defines the black hole in space. At the very heart lies the second component, the singularity. It's where all infalling matter is crushed. The singularity is a point of zero volume. It has infinite density. Here the laws of physics, including Einstein's general relativity, break down. A significant challenge arises when we try to study black holes. How do you take a picture of something that emits no light? We don't see the black hole itself. We observe its effects on nearby space and matter, like detecting wind by watching leaves rustle. NASA and partners observe wavelengths beyond human sight. One powerful method is the accretion disk. Gas gets pulled inward, dust gets pulled inward, entire stars can get pulled inward. They don't fall straight in. They're whipped into a flat, spinning disk, like water swirling down a drain. Friction and gravity heat the disk to millions of degrees. It glows in X-rays, NASA's Chandra. Observatory detects that X-ray light, mapping X-rays pinpoints supermassive black holes and how they feed. Another method is watching star orbits. At the center of the Milky Way lies Sagittarius. Decades of telescopes track stars near it. They've seen stars orbiting incredibly fast. Tight paths around, nothing. No visible object could be that massive, about 4 million times the Sun's mass, strong evidence for supermassive black holes. The most groundbreaking was the 2019 EHT image of a black hole's shadow. Radio telescopes across the globe worked as a virtual Earth-sized telescope. Now we move from the observed reality of black holes into the realm of pure theory with the idea of a wormhole. A wormhole, also known as an Einstein-Rosen bridge, is a speculative structure that could link two very distant points in space-time. The concept emerges directly from the mathematics of Albert Einstein's theory of general relativity. In essence, it proposes that the fabric of the universe could have shortcuts, like secret passageways in a vast castle. Instead of traveling the long way across a cosmic map, a wormhole would allow for near instantaneous travel from one point to another, potentially even to another universe entirely. To help visualize this, let's use a classic analogy. Imagine that space-time is a large sheet of paper. To get from a point on one side of the paper to a point on the other, you would normally have to travel all the way across its surface. But what if you could fold the paper in half, bringing the 2 points right next to each other? A wormhole is like punching a hole through the folded paper, creating a three-dimensional tunnel that connects the 2 points. While the idea of zipping across the galaxy through a wormhole is an exciting prospect, the physics behind it presents enormous, perhaps insurmountable, challenges. The first major problem is stability. The original Einstein-Rosen bridge is now understood to be incredibly unstable. It would pinch off and collapse into a singularity so quickly that not even a single photon of light would have time to pass through it. Anyone or anything attempting to traverse such a wormhole would be crushed in an instant. This makes the classic wormhole model completely impractical for any kind of travel. To overcome this instability, physicists propose a special substance. This hypothetical material is often called exotic matter. It would need negative energy density, generating a kind of gravitational repulsion. Normal matter with positive mass and energy curves space-time inward. To hold a wormhole open, you'd need something that pushes space-time outward, anti-gravity. We have never observed exotic matter in required quantities. Quantum effects like the Casimir effect create tiny regions of negative energy density, but they are a far cry from the vast amounts needed to stabilize a macroscopic tunnel. Without it, a traversable wormhole remains a mathematical fantasy. Intense radiation could flood the tunnel, and extreme tidal forces could tear travelers apart. So NASA focuses on observable phenomena we can actually test. If we are to complete our journey into the theoretical extremes of space-time, we must discuss the most elusive member of our trio, the white hole. In simplest terms, a white hole is the mathematical opposite of a black hole. While a black hole is a region that can only be entered and never left, a white hole can only be exited and never entered. It is a cosmic fountain, a place from which matter and light are continuously and unstoppably erupting. Nothing from the outside could ever cross its event horizon to get inside. The concept arises from the same equations that predict black holes. Solving them reveals a time-reversed solution: push instead of pull. Black holes exist for all future time. White holes would exist for all past time. But unlike black holes from collapsing stars, white hole formation is dubious. They seem to violate the second law of thermodynamics by decreasing entropy. Though once invoked for phenomena like gamma-ray bursts, evidence is lacking. A black hole to white hole pathway via a wormhole is an exciting idea, entirely unsupported by data. As we have journeyed through these three incredible concepts, it is helpful to summarize their key distinctions. Though often grouped together, they play very different roles in physics. First, evidence. Black holes stand on solid ground. Stellar orbits, X-rays from accretion, and the EHT's shadow image. NASA missions continuously confirm their presence and behavior. Wormholes and whiteholes are entirely theoretical. No observations. Function and behavior. A black hole is an eater. Its horizon is a one-way membrane pulling matter in. A whitehole is a hypothetical giver. Matter only exits. A wormhole is a connector, a bridge linking distant points. Physical plausibility. Black holes form naturally from massive star collapse. Traversable wormholes require exotic negative energy matter, highly improbable. White holes likely violate thermodynamics. Summary: black hole, eater; wormhole, connector; white hole, giver. Our exploration of black holes, wormholes, white holes brings us to the very edge of human knowledge. It is where observation meets theoretical physics. We have seen that black holes are confirmed and fascinating, shaping galaxies. Wormholes and white holes remain beautiful ideas born from mathematics. Science closes the gap between imagination and reality. Black holes were once dismissed as a quirk until evidence arrived. With powerful new telescopes, we confirm the incredible. This history teaches hopeful patience. Organizations like NASA and partners are our scouts on the frontier. From JWST to future gravitational wave observatories, we gather more clues. Each dataset and image helps refine theories and ask deeper questions. We may never find a wormhole, but the search could reveal new gravity. Let us keep looking up. Let us keep asking why. The journey is the destination.